Hello everyone, and welcome to today's webinar. The topic of today's webinar is motion capture dataset of 137 post-operative total hip replacement patients, current and future applications. My name is Divyax Chander, and I work as a sales engineer here at Anybody Technology. Today, I will be the host of this webinar, and I will be joined by my colleague, Christopher Iverson, during the Q&A session in the end. In the Anybody webcast series, we host a variety of presenters who have used Anybody modeling system in different applications. In today's webcast, I'm very pleased to introduce our presenter, Dr. David Lunn from Leeds Beckett University. David will present his recently published open access motion capture dataset of 137 post-operative total hip replacement patients. The session will outline the structure and scope of the dataset and discuss current applications and future opportunities in musculoskeletal modeling, clinical biomechanics, and preclinical testing of implants. David's dataset is already published in Nature, and you can also access an associated Anybody model repository to process the dataset. The presentation will start in a few minutes or so, but just before we start, I will give a general introduction and overview of Anybody modeling system for those of you who are unfamiliar with the software or musculoskeletal modeling and simulations in general. First of all, I'd like to draw your attention to the control panel. The control panel appears on the top right side of your screen. You're welcome to submit questions and comments via the questions panel during the presentation, and we will try to address the questions at the end of this webinar. In case we do not get to answer all your questions, we will try to do so by email within a reasonable time. So let's begin by having a look at what Anybody modeling system actually is. Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data and forces, and as output, it calculates internal body loads such as joint reaction forces, muscle activity, and metabolic energy. Anybody is used in a wide variety of areas and applications, and a few examples of these are movement analysis, product design optimization, sports optimization, orthopaedics and rehabilitation, ergonomics with and without assistive devices such as exoskeletons, and in the automotive industry. The typical workflow in Anybody could look like this. You provide the recorded motion data as input and use the body models which you or others have built. And then you can optionally provide some kind of environment, which could be a special type of equipment or, for example, an exoskeleton. Then you can use Anybody to combine these things and run the inverse dynamic simulation, which solves the muscle recruitment problem. This basically means that we go from motion to calculating the internal body loads and interaction with the environment in some cases. You can then output the results and use it for post-processing with, for example, some kind of finite element tool, but many users also close the loop completely by doing some kind of design optimization and then run the cycle multiple times. This actually brings me to the end of the introduction, and I will hand over the word and presenter role to David now.
So thanks for the introduction, and thank you for the invitation to talk about the recently published data set that we published a couple of months back. And thanks for those that are joining us or those that are listening back to this on YouTube or through the Anybody website. I'm going to talk around the paper that we released, and more importantly the data sets that's associated with it. So my name is Dr. David Lunn. I'm a senior lecturer at the senior lecturer in musculoskeletal biomechanics at Leeds Beckett University, the Carnegie School of Sport. So I know we've already just seen a bit of a screenshot of the dataset title on the previous slides there. So the dataset, as a journal article, has a lot of information in terms of the background of the data that we've collected, how you can find the data, how you can use it, how you can access it. But the actual data is held in a research data repository held by the University of Leeds, which is what you can see to the left there. So there's probably the two important parts of the data set in terms of finding it. On the next page, this slide here, the links in the bottom, how you can actually access the data directly without going to the paper. But again, please read the paper, as it has got a lot of technical details in there around the use of the data and what the data means. When you do go to these websites, so into the research data repository, there's a number of different files, but the main ones that you'll be looking for will be the C3D and text files. Then we have 2 Excel spreadsheets as well, which are the participant demographic spreadsheet and one spreadsheet containing the trial information. So within the C3D files and text files folder, once you download it and unzip it, you'll be presented with a series of folders that you can see on the left of your screen here. So in terms of what the LLJ stands for, that is for LifeLongJoints, which was the project that was associated with when we collected this data, and I will talk through that in a few slides' time. And then the number is just the patient identifier. So the first one is LifeLongJoints patient number 1. You'll see also that we've got a version control after that as well. So you've got v1.0, some of them are v2.0, so version 2. And this is where we did release a subset of the data set previously, so those patients with a version 2 of the more updated files in our previous released data set. So within those folders then, we have got the C3D files for all the different activities of daily living, plus the static trials as well, again, which I'll talk about in a few slides' time. In addition to the C3D files, we've also got the text files too, which contain basically the same information, but make the files a little bit more accessible if you haven't got access to motion analysis software where you could run your C3D files. Within those files, whether it's the text files or the C3D files, you have you've got some marker trajectories in there, you've got the data regarding the force platform, so the analog signals. You've also got some gate events in there. And in addition, you have some metadata as well regarding the patient characteristics, which I'll show you a little bit more in the next slide too. So hopefully that just gives you a good idea of where you find the data and what's actually contained in those folders. In the Excel spreadsheets, then we've got our first one, which is the participant demographics spreadsheet. So this contains information on all of the patients that we collected and all of the C3D files that we've released. So in total, like the title gives it away, is there is 137 patients. In this spreadsheet, you've got information such as when that data was collected, which again feels a lifetime ago now, alongside some of the demographic information, so their mass, their height, BMI, which leg was operated on. So we did capture some unilateral and bilateral patients. We've also got the age of the patient, as long as how long it was after the time they'd had a total hip replacement that we actually collected their data. And this was collected typically between 1 and 5 years post-operative. In addition to that, you've also got the number of trials that are available per activity of daily living. You'll see that this does vary patient to patient. And the reason for this was there's multiple reasons. So one, it could be that the patient was unable to complete the tasks that they were asked to do. Another one was it could have been time dependent. So if we spent a long time with the patient on the early activities of daily living, then we maybe ran out of time with the patients to collect that data. So that's why there's some discrepancies between numbers and the number of patients. So in addition to that participant demographic information, we've also got an Excel spreadsheet with trial information. And this trial information is really important in terms of associating which static trials belong to which dynamic trials. So in terms of our workflow and the way we collected the data, the patients were asked to do a static trial first, in which all markers were placed on the patients, and then to help the sort of the natural movement of patients, we did remove some of these markers, or sometimes they fell off, but that didn't matter because in the dynamic trials we kept the important ones that we were able to track the movement of their patients. So it's important that you recognise that some of the dynamic trials are associated with specific static trials if you're using these in the future. Similarly, if more markers than what we required did actually fall off, then we would have to redo a static trial, and in doing so, we'd reassociate those with the dynamic ones. So that's all the information there in terms of the spreadsheets, which are important for those post-processing aspects of the data. So I thought I'd start off with that just so you've got a bit of an idea of what the data is that I'm going to be talking about. But now I want to put some context on how the data was collected, why we chose the activities of daily living, why we chose these patients to collect data on. And this project was part of a large EU program grant called LifeLongJoints. And again, like I said previously, it seems like a lifetime ago that we're working on this, but it was a really enjoyable program that we worked on across multiple different partners across the EU. It was led by Professor Richard Hall, and the area that I was working in was led by Professor Anthony Redmond at the time. Professor Richard Hall now is down at the University of Birmingham, but when he held this grant, it was at the University of Leeds. So the idea of this project was to try and improve how long total hip replacements last. To do this, we tried to improve the coating to reduce the wear of these implants. So the rationale behind it was the fact that actually primary hip replacements are increasing year by year, and in 2024 there was 116,000 just in the UK alone, according to the National Joint Registry. And we know that joint replacements were lasting, although successfully, at 5% at 15 years, but this increases at 20 years. So they weren't lasting the full lifespan of our patient population. And at the time, this was primarily down to wear as a cause of the problem. So we get wear of the implant, this causes osteolysis, this causes loosening of the implant, and that causes an extra revision. Although I know other causes are very much the focus of a lot of the research that goes on at the minute, such as periprosthetic fractures, but still wear was still a big component of reasons why these revisions were taking place. And interesting for us in the work that we were going to do, where it was actually in working with the patients, is that we know revision rates were actually linked with patient characteristics. So you could put the same implant in a 50-year-old male, and you could put the same implant into an older female, and actually their revision rates would be different. But actually no one understood why. We didn't really recognize why they would be different, and we certainly didn't predict it at the time of putting that implant in. There has been some great studies to show this actually as well. So if we're looking at the lifetime revision risk of patients, we can see there is differences between male and females, and also differences between different age groups as well. And this was a study done by Bayliss in the Lancet in 2017. And actually using the most recent data from the National Joint Registry in 2025, we still see those differences exist. So we still see a different revision rate across males and females, and actually over those different age categories too. Similarly, we see differences in patient demographics such as BMI. So in this study by Culliford et al. In 2013, he stated that for every 1 BMI unit, there was a 2% increased chance in revision risk. And again, we don't know why this is. Is it due to an increased load? Is it due to the fact that patients potentially with a higher BMI actually function differently to those patients? And this is some of the work actually we're conducting at the minute, trying to understand how patients living with obesity walk and move compared to those who don't live with obesity. And hopefully that's going to help us understand a little bit more about that changes in those revision rates. So actually, when we looked at this data, we looked in the literature, we recognise that actually we do know that these patient characteristics do affect the revision rates, and they do change how long patients have a joint replacement form when they need that revision. But what we started to question was actually, why can't we predict this? Why aren't we predicting this at that preclinical level? So we looked back to actually how preclinical testing is done and what testing is taken part, particularly with wear. And I know the standards are used for other aspects of preclinical testing, but we were focused on that aspect, which is actually the ISO 14242 waveform, which is what you can see on the screen here. And when we look at this, we can see that actually it does represent somewhat of what the hip moves like during a gait cycle. So we've got the flexion extension in black, we've got the ab and abduction in green, and then we've got the rotation in blue there. And alongside this, we get this sort of 3 kilonewton axial force, which represents sort of a ground reaction force contact. But actually, when we look at this and we start to scrutinize a little bit more, we can see that it's quite a stylized movement. We see that it's only for walking as well, when we know patients actually do more than walking. And when they undergo this test at that time point, they only undergo 5 million cycles, which is around about the equivalent of 45 minutes walking for 1.5 days. And we've already just said earlier that these patients are living with these joint replacements for around about 20 years. So testing it for 1.5 years maybe isn't adequate enough to show where those changes are affected during different patient characteristics. And when we look a little bit deeper, we can see that this waveform was actually derived from patients who don't have total hip replacements, and actually are from a quite a healthy age. So I don't know too many people with a joint replacement that are around about 22 years old. And again, at the time, this was great in terms of Paul's study in 1967, but actually we're able to collect much more specific data now. So our role and our thought here was actually we can do better than this. We can start to improve preclinical testing using much more specific waveforms to the people using these joint replacements. So within the LifeLongJoints project, there was 7 different work packages, and the work package that we were leading was work package 2. And our main task, our main deliverable, was to develop new, more representative waveforms which could be used for preclinical testing. And we wanted to allow this to meet 2 criteria. So the first one being, we wanted this waveform to be patient-specific. So we wanted it to be used by the patient. We wanted it to be reflective of the patients that actually use these joint replacements. So we want to reflect their patient demographics and their load profiles. And in addition to that, we wanted to make it patient relevant. So we wanted these waveforms to represent the patient population and their activities of daily living that we're performing on a day-to-day basis. So rather than just going for what seems a little bit tokenistic as let's just look at a walking cycle. So this was our role. And within our work package, it wasn't just me doing this work. It was a very collaborative team effort, and it was easily one of the most enjoyable projects that I've worked on. Mainly onerous to the people that I was working with and the collaborative nature of that. So this, in a nutshell, was our work package. So in the middle, there was me working at Leeds Teaching Hospital Trust, collecting the data on our patient population, and then working alongside Martin Lunn and Casper, who was at Anybody Technology at the time, and then working with our team from ETH Zurich, so namely Dr. Enrico De Bieri and Professor Stephen Ferguson. We were very much working on improving the model and then applying that to the data set that we were collecting in the lab. So then once we create these waveforms, like I said, these were to be used for preclinical testing, both in vitro testing, which was done by a purpose-built simulator that was able to produce the waveforms and actually reproduce the waveforms in vitro testing. This simulator was held at the University of Leeds at the time and produced by Simulation Solutions, but has now since moved with Professor Richard Hall and Professor Michael Bryant down to the University of Birmingham. And then in addition to this in vitro modelling, we're also conducting some in silico modelling down at Imperial College with Professor Rob Husing and Dr. Lehman Gao, who's now at the University of Nottingham. So this was our LifeLongJoints work package. Like I say, the work was done in a very collaborative way, and some of the results that I'm going to show you was very much the work of our team, namely Dr. Enrico De Pieri and the guys at Anybody too. But I'm going to go into the data acquisition bit, because this is the data that you'll receive, that has been released as open access through the Nature Scientific Data Journal article. I did want to start a little bit with just looking at how we recruit our patients, because I think it's often forgotten in terms of how important it is that we get our patients into the lab and they allow us to use their data. And actually the work that goes into recruiting the patients is quite large. So we were fortunate to be working at Leeds Teaching Hospital Trust, where they were seeing around about 1,000 total hip replacements per year. And we were able to access that database to allow us to try and recruit those patients. So the way we recruit these patients was we essentially looked at the database and sent everyone within that database who'd had a total hip replacement between 1 and 5 years and asked them if they were willing to take part. And that's the actual letter that you can see on the screen there. And we asked them to call if they were interested. And to be honest, the response was quite overwhelming. We received well over 400 phone calls. And the office was, to the dismay of my office workmate at the time, the phone call was the office was quite busy with phone calls, which kept us both quite busy for a number of weeks and months. But again, we were really grateful for all those patients who were willing to take part. And it's also worth mentioning now that we did have quite a strict inclusion criteria in the fact that we wanted no other joints replaced other than their hips. And we also wanted them to be no pain, so it almost needed to be a really well-functioning joint replacement, and also no other conditions that affected their mobility. And actually, when you're working with an elderly or an older adult population, that's quite difficult to do. So we ended up actually excluding more than half of the patients who ran, which did pain us a little bit, given the fact that they were willing to give up their time to be included in the study. But it just meant we were able to control the group of patients that were seen, and they were able to conduct all of the activities of daily living that we'd asked them to do. So we did actually recruit into the study 155 patients, but once we got them into the lab, there was a number of reasons why we couldn't collect data. Some of them actually couldn't conduct the activities we were asking them to. Others, the data was lost because some of the markers dropped off and then we didn't notice them. Again, taking responsibility for that, as can happen in the lab sometimes. And also, when some patients attended, actually they did have other conditions that they didn't relate to us over the phone as well. So that's where the 137 number comes from. It does pain me that it's not a little bit more of a round number, but it's a number we'll always remember in terms of the data set. So that at the time, this was a good number. This was a large number of total hip replacement patients that we've been able to collect data on. And the reason we set out to do this was because, again, if we take you back to the slide where we set out with the goal, we wanted to make this reflective of the patients who use the joint replacement. And that didn't include people. We didn't just want to get that down to a single mean to look at one single waveform. We wanted to look at the different patient demographics. So this included things like age, BMI, their function, and other surgical factors too. So we were trying to stratify the patients to these different groups. So in terms of data collection, then this is our laboratory at Chapel Allerton Hospital, which is in North Leeds in the United Kingdom. At the time, it has been updated since, but we had a 10-camera Vicon system and 2 AMTI force plates that were embedded into the ground, which you can see just in that ground on the image there. For the other activities of daily living, such as the stair climbing and the sit-to-stand, we did have some other equipment in situ. So on the bottom of the image, you can see our instrumented stair force plates. So essentially, they worked on a cantilever beam that were bolted into the force plates on the floor. I must say, I took this image and I asked ChatGPT to tidy up the background, and it's done a great job. I don't think I've ever seen the lab this tidy, but I don't think it ever will be either. Just as a biomechanics lab should be. And in terms of the sit-to-stand, we also used a bed hoist essentially with a chair attached to it, so that we could normalize the height of the chair according to the patient. So we looked at essentially line up that chair with the patient's tibial tuberosity, so we could differentiate between source rather than using the standard chair height between the smaller and taller patients. And in terms of the marker set that once our patients were into the lab and they were consented in, we started to place our markers according to the CAST marker set, which is a series of different anatomical markers and also some tracking clusters too. The way this marker set works and the way we process the data was that actually we placed the anatomical markers, and then when we were building the model, we assigned the tracking markers in reference to where these anatomical markers were placed, so that during the dynamic trials, all we actually had to do was track those tracking markers, so those clusters that you can see on the thigh and the shank. So in the dynamic trials, when you look at the C3D files, you see that a number of the markers were actually removed, so particularly around the knees to allow participants to walk more naturally. And also, if some markers fell off, as long as we had 3 markers per segment, then that was absolutely fine for us to continue that data collection. And I'll get onto in a second about how that might affect the modelling and how we sorted that within the Anybody modelling system. In addition to the standard sort of CAST marker set, we had 6 upper body markers. Again, this was to help the musculoskeletal modelling, so we could track the position of the trunk to give us some more realistic joint contact force data. And then we also had some additional calcaneus markers for some of the stair trials as well. And this is because we recognised early on that the markers on the calcaneus were getting obscured, particularly during stair descent. So we added some additional on, so we could track the foot a little bit better. And again, all of this information regarding the markers is within the manuscript, And if you've got any questions about how the processing works, then feel free to give me a call or drop me an email. So once we've collected our data, we set about asking our participants to undertake the activities of daily living. And we did look at sort of 7 main activities of daily living. So we had some walks, we had some lunges, some stair ascent, some stair descent, as well as some sit-to-stands squats. In addition to that, we did have some more adverse conditions, such as a jump and a jog, if our participants were able to do those and sort of do those routinely. But we didn't collect too many of those, but they are within the C3D file collection. The numbers are on the right, as you can see, the number of walking trials that we collected. And as you can see, as we got to the more demanding activities, actually the number of trials dropped off. And again, this was due to our patients not being comfortable in being able to conduct those tasks, or if we just ran out of time as we progressed through it. To put it in context, the participants were probably with me for anywhere between an hour to 2 hours, because we did have a bit of a break in the middle just to allow them to fill out some patient-reported outcome measures as well. So we collected things like the IPAC, which is around about physical activity. We looked at also the Oxford HIP score as well. And this is something that I should mention now that we probably will add to the data repository at a later date. So after we'd collected this data, this was our inverse dynamics, and we knew we'd collected some nice data to be able to just publish off the back of this without any actual musculoskeletal modeling data. And these were a number of the studies that we collected, some just looking at the hip kinematics and kinetics, stratifying by their age and functional capacity. Other studies looking at things like the dynamic acetabular cup orientation, which was conducted by Ksenia Vasudjeva when she was a PhD student at the University of Leeds. And I just want to talk a little bit around some of those results just based off the inverse dynamics data. So one thing we noticed as we started to collect our data and look at the analysis, we started to notice that actually during the normal walking activities, we found that we've seen sort of the trends that you would expect to observe between the different age groups. So we stratified our patients into sort of different age categories and looked at their hip kinematics. And we did notice sort of that traditional trend of you'd see a reduced gait speed in the older populations, a reduced peak abduction moment, and reduced extension and excursion around the joint angles. But actually, when we looked at these same strata, so the same age groups, but at a more demanding activity such as fast walk, we noticed that the differences were different. So it's suggesting that actually, like the older populations or the older adults were able to walk quicker when you ask them to do, suggesting that what we typically do is say that age is a good indicator of function, whereas in reality we weren't seeing that. So we considered how we might be able to stratify these patients in a more reflective way. And we looked into the literature and we've seen that actually we could use gait speed as a good indicator of function. We know that the sort of World Health Organization have tried to query it as the sixth vital sign. We know that in some conditions such as Parkinson's that we see that change in gait before many other symptoms as well. So we wanted to see how this would be reflected in our patient cohort. So what we did was we created 3 groups of patients. The first one was our normal or homogeneous group. And these are patients who walked within 1 standard deviation of our main gait speed, which was in our cohort 1.1 meters per second. We then looked at our low functioning patients and we classified these for anyone who walked at a gait speed of less than 1 standard deviation of our mean gait speed. And then we grouped a high functioning group with patients who walked at greater than 1 standard deviation of our mean gait speed. And these turned out to be our 3 groups that we stratified them to see if this was a better indicator of their function rather than age. We also compared these to our healthy control group too. When we looked at the results, if we just focus on very quickly on gait speed, for instance, so on the image here, the blue line is just their normal walking speed, normal walk, and the orange line is their fast walk. We can see that when we stratify by age, that actually during the normal walk, as we observed earlier, there is quite a strong relationship between age and decline in gait speed. But actually during the fast walk, there is a reduced strength of this relationship, suggesting actually our older patients or older population were able to walk quicker when asked to. But when we look at our new strata, I mean, as we expect, given the fact that we have categorized our patients based on this during the normal walk, we see that our high functioning are obviously that there is a very strong relationship between our low functioning walking slower, high functioning patients walking faster. But when we look at the same strata and they remained in them same groups for our fast walking trials, we see that that strength of relationship is maintained, suggesting that when our patients needed to and required to, they're able to sort of maintain that walking speed, suggesting that gait speed is a better indicator of function than just categorize our patients by their age group. So again, this was just very much based off the inverse dynamics, but the aim of our work package, again, just to revisit this, was to create some waveforms, and we can't do that just using joint moments and joint angles. So to do this, what we needed to do was to employ some musculoskeletal modeling. And like I've said, luckily for us, Anybody Technology at the time were a partner in the project, which gave us great access to the support that they provide, which was a massive help. Alongside working with people like Enrico and Steve Voos at Zurich, we're able to generate these waveforms ready for a simulator to do some preclinical testing in vitro. I'm not going to talk around this too much because I know Dr. Enrico Duperi has done a webcast on this, but actually we didn't just take the off-the-shelf model. Enrico works hard alongside Morton Lunn from anybody at the time to develop the model and refine the model so we could get this nice validated model that we could use to take forward to the large cohort. Like I said, it's very much Enrico's work where he changed the moment arms, changed the lines of action of those muscles to compare it to some of the Bergman data out there, which is a nice study that you can see in the top right of the console. Please feel free to visit that. And I think it was mentioned at the start about this data set, and the models are actually available on Zenodo, which I'll mention a couple of times. And these are the models that actually are available that Enrico produced as part of this model. So once we've got this model that we're happy with, and we were happy with the validation work that we've done, we applied this to all the participants that we collected within the lab. And you can see these on the screen now. So we applied these to all 8 activities of the living, if you're counting sit to stand as 2. And it was nice to see actually the differences in the waveforms even without looking at the ISO standards. So we could see that there was variations between our locomotor activities, which you can see at the top left, so our walk, fast walk, ascent of stairs and descent of stairs, and alongside our non-locomotor activities such as the squat, sit, stand, and the lunge too. I'm not going to talk around these results too much, but again, the papers that were published are on the screen based off this, and we also looked at how things like BMI and age and function also affect these different waveforms. One thing I did want to talk a little bit more around is actually the patient variability that we see within our patient cohort. And I think this is really important in terms of I think where a lot of the data is going in terms of trying to get this sort of stylized waveform that we do see in the ISO standard, and after we do present in the papers that we've published. But actually, it's important that we don't lose that variability. So what we've got on the graph here on the left is our walking trials. So they're all the trials by all our patients. And on the right, we've got our sit-to-stand trials. And actually, it's important, and again, I think these are probably my favorite graphs. I'm not sure everyone has favorite graphs, but I do. And the reason for this is because it truly reflects the variability we see in our patient populations. And something that we don't observe, particularly in the sort of ISO standards, whether these really stylized, almost perfect waveforms. And when we question ourselves about understanding why we don't see this variation in or being able to predict wear patterns, and I think it's probably because we lose this variation that we see in our general population. So what I hope for going forward is that some of this variation is taken into consideration when we're doing some preclinical testing, if we're not going to do too much of a disservice to our patients. So moving on from this then, and again, we do see this patient variability in some of the other analysis that we do. We wanted to analyze the data in a slightly different way too. So we weren't just happy looking at our sort of single waveforms. We wanted to understand what's actually happening on that contact surface level. And again, Enrico developed this really nice method whereby we were tracing the force vector across the acetabular cup to understand where those high contact forces were, and also the shape of those force vectors too. The images that you can see on the top right are the dark patches where the high contact forces are, and the lighter colours are where the lower contact forces are. The coloured parts are the mean of all the patients, and the other lighter parts are so the sort of the grey scale is sort of individual patient patterns. And you can see actually there's quite a lot of individuality there, so there's a lot of variability in the movement patterns. And also we see a change across the different activities of daily living. So we see that there's quite a nice figure of 8 pattern within our fast walk and normal walking. And when we move down to our stair ascent and stair descent, so the red and the green images, we see there's a sort of a change in that location of the force vectors, and where they would act on them as a tabular cup. But actually it's more interesting when we look at the sort of non-locomotor activities in terms of the location of those force vectors. So we see that we get a much more linear pathway when we're looking at things like a stand and a sit movement, which are the top two, and also similarly in our squat and lunge activities too. We get a change in the shape, but we also get a change in that location. So the force vectors become much more posterior and much more inferior compared to our walking activities. And the interesting part for me here is how close we're actually getting to that edge. And we know edge loading has been linked with these increases in wear. So actually this gives us a good idea about what activities might be putting patients at risk of potentially increasing that edge loading as well. And again, you can read more about those papers and those results in the paper below. I did mention this a little bit earlier, but when we were releasing our data set, we were quite keen to make sure that people were able to actually run the musculoskeletal models too, and not just the C3D files and the inverse dynamics, which is all you're sort of really getting with the release data set. So Morten and Enrico and Casper and myself set about setting up our data repository in Zenodo, where essentially this should be able to plug into our C3D files and use the musculoskeletal modeling with an anybody license too. So these files and the folder structure are all set up in exactly the same way that we conducted our studies. So they have the same environments, same marker names too. So hopefully that should help people sort of run those musculoskeletal models if they wish to do so. In addition to the papers that we've published off this data set, other people that are a little bit more removed from our group have used the data, and it'd be great to see a little bit more of this now that we've set the data set into the public domain. So Lorenzo Mattei actually requested some data from us a number of years ago, who work at the University of Pisa, and they looked at doing some in silico modeling and some in vitro testing and comparing it to the ISO standard, which was a really nice paper. So feel free to have a look at those and hopefully get a bit of inspiration how we could potentially use this data in the future. And similarly, Ben Clegg from the University of Leeds, he looked at using this physiological loading on and activities of daily living on the wear of metal on polymer total hip replacements through some in vitro testing. So hopefully this might give you some ideas how you potentially could be using the data and how some groups are already using that. I did mention some of these future applications within the publication itself, but I did want to touch upon them a little bit more closely as part of this presentation. So I'm hoping that actually the data set that we've released will go some way to improving the preclinical testing. I know it's not as simple as saying, oh, we'll just use this waveform, given the fact some of the simulators can't actually do the excursions and the forces that we ask of them and what patients actually do. But hopefully, now that the data is there, this will go some way for people being able to do that. And I know this is some ongoing work by Professor Richard Hall, Professor Mike Bryan, and Dr. Rob Beadling down at the University of Birmingham, using the simulator that was made as part of LifeLongJoints to be able to run these simulations and hopefully look at how patient-specific loads and patient-derived loads actually do produce different wear results compared to the current ISO standard, which might give us an indication of whether we're able to predict those patients that might have a more successful outcome compared to others. Similarly, I think this is something we've touched on, and I know myself and Enrico have talked about this a little bit in terms of could we use our contact force pathways for pre-surgical planning. This is already undertaken from more of a structural perspective, where we can look at the radiographs and look at those patients that might be more susceptible to edge loading and help to address the placement. of the components of the joint replacement. But actually, alongside that, could we use some of the patient's kinematics to really understand how those placements could help to save those participants that might be more prone to edge loading due to their joint kinematics during walking, during activities of daily living. And then finally, with any sort of large data set, I think people might use this for training models or benchmarking against. And again, this is a really exciting area for me, the fact that hopefully we'll be able to use this data to help predict patient outcomes. Any machine learning approaches that are already out there, could we use our data set to benchmark algorithms? I'm certainly no expert in these areas at all. I'm probably a little bit of a novice in those areas, but I do see the use for that. And I think one thing that's important for me is that are we able to quantify some of that variation? I think again, this is the bit is we've probably not been able to predict what patients do is because of the variation between them. But I do wonder whether there's a lot of work that needs to be done to understand this variation, being able to characterize them, and hopefully and establish some normative range within the strata of our patient population too. And then just the final couple of slides from me. So again, I'm always keen to collaborate, and a lot of my most enjoyable work is done through has came from collaborations with people. So feel free to reach out to me either through email or my LinkedIn. And again, just a bit of a plug here for some of the work that we're currently doing. So PhD student Mason Salichu is doing a fantastic job analysing Achilles tendon ruptures using dynamic ultrasound and some of the methods that you've seen today. We'll be presenting his work at ESMAC in Maastricht and Hasselt in 2026, September this year. And also I'll be presenting some work that we're currently working with two surgeons looking at pre and post-operative gait changes in adolescents who have undergone total hip arthroplasty too. Unfortunately, I can't make World Congress of Biomechanics, otherwise it'd be great to catch up with some people there too. Then finally, I'd just like to thank the people that I work closely on this project. So namely at the University of Leeds at the time, was Professor Anthony Redmond, Dr. Graham Chapman, who is now at University of Lancashire. The guys from University of Birmingham, which I mentioned on the previous slides. Thanks to Anybody Technology for their help in developing the model, particularly Casper and Morton. And then finally to my colleagues at ETH Zurich, and now Enrico is currently at the Schultes Clinic, but Dr. Enrico Di Pieri and Professor Steve Ferguson too. And then just thanks for EU for funding the work, and also the NHR for supporting us during the work too. Thank you for listening. I guess just to finish, a big thank you to the patients who took part. And again, while we did collect a lot of activities at daily living, we didn't collect everything. And as one of my patients reminded me that she does dancing 4 times a week, so I should be measuring that if that is an activity of daily living. And be good to dance in the lab, so I decided to record her, which gives them a nice sort of final slide to finish up. So thank you very much, and thanks for tuning in.
Yeah, thank you very much for this great presentation.
Thanks.
So just before we go to the Q&A session, I'd like to say a few words about our online resources and upcoming events. If you want to know more about Anybody Technology, you can check out our website, anybodytech.com, where you can find different events, special dates, and previous webcasts. You can also check out anyscript.org, which is our community website for people using Anybody. Here you will find multiple online resources such as our wiki page, several blog posts, and links to the repository sites. Our forum is also located on anyscript.org, and here you can ask questions and get help from some fellow Anybody users. I would also like to mention a couple of upcoming events. So on June 24th and 25th, that is tomorrow and day after tomorrow, we are hosting Anybody Solutions Days, where you can book a 30-minute online meeting and get support from one of our engineers. There are only a few slots available now, so please hurry up to book them. Anybody Technology will be present at the World Congress of Biomechanics in Canada in July. You are welcome to visit us if you are going to be there. To end this presentation, I would like to mention that we maintain a publication list of papers using Anybody modeling system and a library of previous webcasts. These are great resources if you want to get inspiration on how to use Anybody. This brings us to the Q&A session, and we will read some of the questions from the audience. So, Christopher, have you had some time to see if there are some questions?
Yeah, so David, you already touched upon it in the very end of your presentation. So mentioning that dancing wasn't part of the activities of daily living. So how did you actually choose the motions that you did?
But yeah, thanks for the question, Christoph. So the main reason, actually, there's sort of a mix in there, really. So the first one is just what we know patients do. So we know they walk, we know they walk up and down stairs. So we're always going to include those sort of primary activities daily living. The other one was actually we wanted to increase the demand on the patients. So looking at things like our squats and our lunges. And the other part was, which I think is really important for any research, is actually we spoke to patients and asked what they found difficult. And it was things like those lunging forward. And actually some of the movements that they were doing were related to some sports that they take part in. So I'm not sure if it's popular elsewhere, but sort of crown green bowling, which is where there's a lot of lunging action takes place. And patients wanted those sort of representative activities of daily living in there. And actually, I didn't mention this earlier in the webcast, but it is something that we got questioned when we submitted our paper, was are they actually activities of daily living? But given the fact we published a few papers calling them that in the past, we were able to fight back on that on the editor's response.
Right, thank you very much. So we have a couple of attendees who's asking about the link to the actual data set. And if I'm not mistaken, it has its own DOI link, right?
Yes, that's correct, yeah.
Yeah, and otherwise I just tried Google it as well, just using the webcast title here, and then you will find your paper and you can go to the data set from there.
Yeah, so exactly. So within the paper, there's a number of different links in there as well to the data set. Or you could be able to search it's called the Research Data Leads Repository. So if you go search for that on Google, then you should be able to search for it. If not, go back to the slides, which I think you'll share anyway, and there'll be the link in there.
Yeah, so I'll process this recording like probably tomorrow, and then I'll put it online, and then you can find the link directly there.
Perfect.
Yeah, there's another question that we have. So is there any additional information that you would have liked to collect it but could not collect in your data set?
Yeah, I think there's a few different ones. I think some around to characterize the patients a little bit better, and some that would have probably helped us inform the musculoskeletal models a little bit more. So I've mentioned that we have collected the patient-reported outcomes. So I think anyone looking at stratifying the patients, they might find that helpful. So I think I will try and put that onto the data repository too. And then in addition to that, we did take a subset of MRI images for a small group of patients. MRI student at the time, Daniel Chadros, he did some work trying to look at actually how the effect of surgery can affect things like the cross-sectional area of those muscles. In addition to that, I wish we did a little bit more strength assessment as well. And again, that would have been really useful to help inform the musculoskeletal models, to make them a bit more patient-specific, I think. So, yeah, but we were restricted with how long we could spend with the patients, and we had to consider that patient burden too.
Thank you, David. Yeah, there's one other question, I think. So with all this data set that you have, do you potentially see that this can be used to develop some kind of digital twins for, by making use of all of these parameters that you have from the patient-specific information and all the outcomes that you can generate from these inverse dynamics analysis? So is there some way to use this data set to make some kind of digital twin? I think that's becoming a bit of a hot topic recently.
Yeah, thanks for the question. It's a really interesting one, actually, because it's something that we talked about at the time. I think we've probably just run out of time to do it in the end. But ideally, what we were looking to be able to do was actually create some sort of platform where you could say, well, I've got this patient. Basically, I'm going to go the long way around and say the answer is yes. I'd love that, to be honest. But yeah, if we could create a platform where you could say, right, I've got this patient who has this BMI, is this age, does this activities, and actually has this sort of gait pattern, what would the best joint replacement be, or how should we best approach this surgery? I think for me, that would be fantastic. I think probably need a little bit more information than the data set we've got, but I think it goes some way to begin that alongside some of the additional information too. So yeah, like I say, long way of saying yes. I think it could be used for making a digital twin.
Yeah, thanks for the answer. Yeah, this is also something that we are interested here at Anybody Technology. So I think if there's anybody in the audience who'd like to maybe collaborate at some point, we're open to these kind of opportunities. Mm-hmm. But yeah, I think we are running out of time now, so we would stop here. Yeah, like Christopher mentioned, we will process the recording and upload it soon. Hope definitely within this week, and with all the links and also the link to the Anybody model, where you can use to process the data set that is available. So yeah, thank you very much, David, for this webinar. I think it's been fantastic, and thank you as well to all the listeners, to the audience. So that is all for today. We will see you at the next webcast soon.
Yeah. Thanks again for the invite, and thanks for everyone tuning in.
Thank you.
Bye. Bye.